Hi, I'm Dan Bauer, and welcome to CVA Office Hours. This is an online forum where Patrick Kern and I talk about issues and techniques that come up in statistical analyses in the social, behavioral, and health sciences. Today I'm going to extend our series on the linear regression model. In the first episode I talked about what is the linear regression model, what are we trying to do there, what are the parameters of the model. In the second episode I then talked about how do we obtain sample estimates of the model parameters using ordinary least squares estimation. And today what I'm going to talk about is how do we make inferences based on our sample regression line to the population as a whole. So just as a bit of a reminder, in the linear regression model, right, what we're trying to do is take a continuous predictor, and I'm going to use an example from prior episodes of experience predicting performance. So experience is going to be our predictor, and performance is going to be our outcome, so our predictor X and our outcome Y, and we expect some kind of relationship between those two variables that's roughly linear, and so we can drop a line in there to show how the expected level of performance varies as a function of experience. And using ordinary least squares estimation, we can calculate our regression line, that's our predicted value y, to be b0 plus b1 x. And so we get our ordinary least squares estimates of b0 and b1, our intercept and our slope, and those estimates are obtained by minimizing the sum of the squared errors. Right? So the observed y minus y hat is our error, and then we square those, we sum them up, and we minimize that sum to obtain our estimates b0 and b1, our intercept and our slope. But ultimately, we're not only concerned with getting the line of best fit in our sample. What we would like to do is make inferences to the population as a whole. And so there are two basic kinds of inference that we make in the regression model. And I'm going to talk about the first in this episode and the second in the next episode. The first kind of inference we can make is whether our model is predicting any variance in the outcome. So does experience have an effect on performance? Do we explain variation in performance on the basis of experience? And so we're looking at the pool of variance in performance and how much of that variance can we explain by experience, and is that relationship significant or not? And this is sometimes referred to as the overall model F-test, or analysis of variance test. And what we're trying to do is look at whether our predictor or set of predictors, there could in more extensive models be more than one predictor, whether those predictors have any significant impact on our outcome. So explaining variance there. So we have the overall model F-test that is based on decomposing variation in our outcome into that which is explained and that which is unexplained. And then we also have individual tests of the regression coefficients. So we'll also have t-tests of each regression coefficient. So for instance, here it would be a t-test on b0 and a t-test on b1. And so we would see whether or not the sample realized values, the sample estimates of b0 and b1 exceed what we would expect by chance if truly the population values beta naught and beta 1 were either of those were 0. So we're going to focus on the overall model F-test this time, and then we'll talk a little bit more about t-tests in the next episode. All right, so one thing that I want to do is when we think about our regression model, so let me just take that off there for a moment. Right, one way of thinking about our regression model is that we're predicting our outcome on the basis of our X variable, our predictor here. And we want to see whether or not we are doing a good job of predicting that outcome. Are we predicting that outcome well, given this predictor experience? And so in the overall ANOVA F-test, that's essentially what we're testing is, do we explain a significant pool of variability in performance that we would conclude that experience has an effect, that the effect of experience exceeds what we might expect to observe only by chance, right? So to do this model F-test, we need a point of comparison. And our point of comparison is, let's say we had a truly lousy predictive model. In fact, let's say we don't know anything at all about the person, right? So we have no idea what their level of experience is, much less anything else. In the absence of any other knowledge, what would be our best prediction for that person's level of performance? Well, we could say, let's just take the mean, right? So let's just say, what is the average level of performance? And that sample mean we'll designate with y bar. right? So in the absence of any other knowledge about the person, my best guess about their performance is average, right? I can't do any better or any worse than that, but that's as good as I can do, right? So I'm just going to say the average. In the analysis of variance for our model F test, what we're going to look at is how much better do we do with y hat equal to b0 plus b1x, how much better do we do when we inform our prediction with our x variable versus if we had no knowledge whatsoever, right? So if we had a model in which we incorporated no other knowledge about the person. All right, so in our regression model, right, we can write our regression model as y equal y hat plus e, right? It's the predicted value plus the error. And what we're going to do now is we're going to see how we can contrast, how we can decompose the variance in our y, the variability in our y, to express it in terms of this mean and the difference of this mean from that predicted value. All right, so we would need to bring y bar into this equation, and we're going to do that by subtracting it from both sides. So we're going to say y minus y bar equal y hat minus y bar plus e. So we've simply subtracted y bar from each side, nothing added, nothing lost. We've simply re-expressed these by adding or subtracting y bar in each place. Now what's the value of doing that? Well, remember, e is y minus y hat. All right, so what we've done here is we've taken the individual's score relative to the mean and we've re-expressed it in terms of the difference between their predicted value and the average. And remember, we're looking to see how much better do we do with the regression line than the overall average, so that's the difference between the predicted and the average, and then the difference between the observed and the predicted, right? So there's our residual. And we can see that graphically, is let's take a particular observation. I'm actually going to remove this one here just so it's not cluttered, but we'll take this particular observation, right? And we can see that here's the mean value for that particular observation. Right? It's the same for all observations, but we'll just put it there so it's in line. And then here's the predicted value for that particular observation. Right? And so what we've done is we've said the distance between the mean value and that observation, we've decomposed it into the difference between the mean, right? So there sits y bar, and there sits y hat. So the difference between y hat and y bar. So y hat minus y bar is this distance right here. And then this distance right here, our residual, is y minus y hat. So we've taken that overall discrepancy between the observed value and the mean, the overall deviation from the mean, and we've decomposed it into these two parts, the difference between the predicted value and the mean, and the difference between the residual and the predicted value. Now, if our regression model is any good, if our predictor is informative in any way, then that predicted value, that black box, ought to be closer to the observed value than the white box, the mean that we would get where we say, we don't know anything other than that, that this is an individual from the same population. All right, so we've decomposed the variability for the observation, but of course we're not interested in just a single observation. We want to be able to say, overall, how is my model doing, all right? And so remember, this piece is how much closer do I get to the observation with my regression model than I would with the overall average. So this is measuring sort of how much better our model is than not knowing anything. And then this piece is what's left over. That's the remainder or the residual. What I'd like to be able to do is say across all individuals, right, this part is large. I'm moving away from the sample average and getting a more informed predicted value for the individual. And this part is small. The residuals that are left over are relatively small by comparison. All right, so for a particular individual, we can decompose the variability, their particular score in this way. It turns out that we can also decompose the overall variability in the sample in the same way. That is, this is additive for the individual, but similarly, the sums of squares are additive. So just as we did the other day with ordinary least squares estimation, where we looked at the sum of squared residuals to pool across individuals to capture the fit of the model and try to obtain the line of best fit, here we're going to calculate sums of squares again. And so we're going to take the sum of the squared deviations from the mean across individuals. So that would be for all individuals in the sample. We would calculate those deviations and square them. And then we would set that equal to the squared deviations of the predicted values from the mean plus the sum of the squared residuals. All right, so isn't that cool? Is for an individual observation, we can decompose their score in this way. Across individuals, we can decompose the variability in the same way using sums of squares. Okay? And it's nice and additive. And sometimes you'll see these referred to as sums of squares total equals sums of squares regression, or some software programs will call it sums of squares model, and then sums of squares error. Or some programs will call it sums of squares residual. It's all the same thing. All right, so the sums of squares total, the overall variation in the data, so all those discrepancies from the mean, can be decomposed into the sums of squares regression, right? So how much closer how far away do we go from the sample mean? That's how much closer are we getting to the observation. And then sums of squares error, what's left over. So a good model would be one in which this is large, right? The model is doing better with the predictor in it, with X in it, than we would have just by knowing the mean alone. So that's large and that's small, right? Because ideally that would be the case. All right, so now given this additive form for the sums of squares, we can calculate a statistic that's widely used in regression analysis, and that's the multiple R squared, the coefficient of determination. Is our multiple R squared. Given this additive expression, what we want to know with the multiple R squared is how much variation in performance, Y, is explained by experience, X. And so we can simply put sums of squares regression over sums of squares total, and that's our proportion of variance due to the model, due to sums of squares regression. So it's a proportion relative to the overall total. So that's our coefficient of determination. And we interpret that as the proportion of variance in performance or in Y that's explained by X, experience. So if we got an R squared of 0.2, for instance, we would say 20% of the variance in performance is explained by individual differences in experience. All right, so we've calculated our R squared based on our sums of squares, but what we'd like to know, let's say we did get an R squared of 0.2, we would like to know whether or not that R square is sufficiently large that we would conclude that in the population, that's a real effect, right? A real effect exists, and that 0.2 wasn't just happenstance, it wasn't just a fluke of drawing a weird sample. And so we want to be able to make inferences, and that R square is really just a descriptive measure of effect size, but we'd like to be able to make inferences and say whether or not our model really is predicting variance in the population as a whole. All right, so we've got our sums of squares. Now what we're going to do is we're going to convert them into what are called mean squares. Right? So how do we do this? Well, we've got to calculate degrees of freedom associated with each one of these sums of squares. And a simple way to think about degrees of freedom is how many unique pieces of information do you have available to you, and then how many pieces of information did you use up, subtract how many you used up from how many you had, and you have the degrees of freedom. All right, so let's start over here with sums of squares total. Is how many pieces of information do we have right here with Y? Well, there are n unique individuals in my sample, and so I start out with n pieces of information, but I use one up by calculating the sample mean. And so my degrees of freedom are n minus 1 for sums of squares total. And then for our sums of squares model, or sums of squares regression, how many pieces of information go in? Well, that's Y hat. Y hat is based on 2 pieces of information, B0 and B1. And so it would be 2, except in a multiple regression model, and we'll talk more about those later on, we'll see that it'll actually be however many parameters go in to calculating Y hat. And so we're going to designate that as P. So P is the number of parameters in the regression model, and then how many pieces of information do we use up? 1, again. All right, so we have P minus 1 degrees of freedom for the sums of squares regression. Now, just to avoid confusion, in some texts and some references, P is the number of predictors. All right, so in this case, that would be 1 predictor, but we are using P, and in other texts, P is used to indicate the number of parameters that are being estimated. to generate y hat. All right, so we have p minus 1 degrees of freedom for sums of squares regression. Now, sums of squares residual, we have n y's that go in, n unique values of y going in, but then we have y hat, and we saw that that was p pieces of information to calculate y hat, and so we have n minus p degrees of freedom. Now look at this, this is pretty cool. Is the sums of squares were additive? The degrees of freedom are additive too. Is n minus 1 is equal to p minus 1 plus n minus p. Is the p's are going to cancel out, and you're just left with n minus 1 here. Alright, so not only are the sums of squares decomposed in this additive fashion, but so too are the degrees of freedom. Alright, so why calculate degrees of freedom? Because to get the mean squares, we have to divide each sums of square by its corresponding degrees of freedom. Alright, so we've got our, take those plus signs out. So we've got our sums of squares total divided by n minus 1 degrees of freedom. And that's going to be our mean squared total. Now, oftentimes you won't see this reported in the regression output. You won't hear it called mean squared total. Why not? Because that's just your sample variance for y, right? Is sum of squared deviations from the mean divided by n minus 1. That's the usual formula for the sample variance of y. Right? So you're already kind of familiar with mean squares. It's just the sum of squared deviations divided by its degrees of freedom. Right? Here, our deviations are the y hats minus the y bars. And again, we're trying to see how far away from the average do we go with y hat as an indicator of how good our regression line is. We're pooling over those deviations, squared deviations, to get a sense of across the entire sample. We divide by the degrees of freedom, and we get our mean squares regression. And likewise, we take our sums of squares residual, we divide by their degrees of freedom, and we get, oops, our mean squared error. Sometimes you'll see that just called MSE, mean squared error. All right. Now, why did I put boxes around these instead of putting plus signs? Is because these are not additive. Mean squared total is not equal to mean squared regression plus mean squared error. So the additivity only works for the sums of squares and the degrees of freedom. It does not work for the mean squares. All right, so why go to all this effort, right? Why calculate all these mean squares and whatnot? It's because we can then take a ratio of our mean squares, and that ratio is going to give us a new statistic that we can use to test the null hypothesis that no variance is explained, that our predictor is useless, and we would like to reject that null hypothesis and conclude that our predictor is in fact explaining variance at the level of the population. So we're going to calculate a new statistic, f, we'll call it f star, and f star is going to be equal to mean squared regression divided by mean squared error. All right, now one way to think about this is as like a signal to noise ratio, as mean squared regression is capturing how much, kind of a explained variance, sort of capturing how much signal is there present in this regression model, and then mean squared error is your noise, right? It's what's left over. Incidentally, we talked the other day about how there's actually a third parameter to the regression model, right, that captures the scatter, and in the population that's sigma squared. In the sample we could call it s squared to not use the population value, and s squared is your mean squared error, right? Your MSE, or your mean squared error. So that's actually another estimate, is the mean squared error, and we'll see it's important for a variety of things, but one thing it's important for is calculating this f star. All right, so we calculate f star, and under some fairly basic assumptions, and we can talk more about assumptions another time, but under some fairly basic assumptions, if there's truly no relationship whatsoever between the predictors and the outcome, then f star is going to have a central f distribution with p minus 1 and n minus p degrees of freedom. So the f distribution is characterized by numerator degrees of freedom and denominator degrees of freedom, numerator, denominator, and we saw the degrees of freedom associated with each of those terms. So under the null hypothesis, f star will have this distribution. Now, we can plot out what does an f distribution look like and it looks something like that. It's an asymmetric distribution. We expect that if there's really no effect, most of those F stars are going to be on the low end, but it's possible that there is an effect and we would see our F star fairly far out. Now, if we saw a regression effect that looked as big as in this scatter plot, we might expect our F star to be fairly far out in the tail. We calculate the area under the curve beyond F star on this F distribution, and if that is less than 0.05, then we conclude we have a significant effect, and our model, in fact, is explaining variance in the outcome. All right, so that's the general idea behind the analysis of variance test, is we want to see whether or not our regression equation is generating predicted values for the outcome that are better than if we knew nothing at all, right? And just by chance, we're going to get some prediction, so we want to see whether or not our F star statistic, our F statistic for the model, exceeds what we would expect simply by chance alone under the null hypothesis. By taking that ratio of mean squared regression to mean squared error, we can calculate a test statistic that allows us to see whether our model is performing better than chance. Right? Now, in practice, what you'll see is in a moment we'll do a little computer demonstration. We'll see what the typical output from a regression model looks like. In practice, what you'll get in your output is a little analysis of variance table that lists the sums of squares and the mean squares and the degrees of freedom and gives you the F statistic and p-value. What people typically report in a typical journal article or manuscript is they'll report the R square for the model as a descriptive measure of effect size. So let's say our R squared in this case is 0.43. And then they'll report the F statistic associated with the model. And so they'll say F, and they'll give the degrees of freedom. So in this case, we would have 1 numerator degrees of freedom because P is 2, and so we have P minus 1 degree of freedom there. And let's say we have 17 people in this sample. Then we'd have N minus P, so 15 denominator degrees of freedom, and then you would give your F star statistic that you calculate, that the program calculates for you. Let's just say it's 17.3, and then after that you would provide the p-value, and I don't know, let's say it's 0.012 in this case. I don't know what the actual p-value would be associated with that F statistic, but the software will compute the p-value for you. So typically, this is what you will report in a given manuscript, but you'll also see in your output that entire analysis of variance table. All right, and so we'll go to a little demonstration. We'll see how that looks.
Okay, so here's the data set we're going to be analyzing today. Again, we're going to be looking at the data set from Ohio State University, where we have as in the first demonstration in episode 1 in this series, we're going to have the variables sex and weight as background variables, number of beers the individuals were randomly assigned to consume, 8-ounce beers. We have their blood alcohol content after the consumption of alcohol, and their road sobriety test performance before and after the consumption of alcohol. In our prior demonstration, we looked at the relationship between beers consumed and blood alcohol content, beers and BAC, but today we're going to look at beers and second sober. So looking at how the consumption of beer impacts your psychomotor functioning. And so, a classic road sobriety test kind of item would be to put your finger on your nose and walk a straight line. The maximum score on the road sobriety test performance is 10, and so lower numbers indicate some degree of potential impairment. Now, these are just the raw data values. To get a better sense of what's going on, we can look at the scatter plot. And so here's that scatter plot of the road sobriety test scores against beers consumed, and you can see that as the number of beers consumed goes up, road sobriety test scores kind of go down. So you can see a negative slope to that regression line. And this regression line was obtained using ordinary least squares, and so we have our estimated intercept and our estimated slope associated with that regression line coming from ordinary least squares to minimize the sum of the squared residuals around the line. Now, what we would like to do is be able to say, this looks like a fairly strong relationship, but admittedly we have sort of a small sample here of 16 individuals, and maybe it's just chance. Maybe this was just a fluke sample where it looks like there's a relationship, but in fact in the population there's no relationship whatsoever. So is the strength of the data here sufficient to conclude that there's actually a relationship in the population? To find that out, we need to run our regression model and look at our analysis of variance table to see how much variance are we explaining and is it significantly greater than we would expect simply by chance. So I'm now going to run our regression procedure. I'm using SAS, but any statistical software program will generate similar kinds of results. So here are the results obtained from SAS. So we have 16 observations, 16 individuals in our sample. And then notice here's our analysis of variance table, and that comes right at the top of the output. And you can see that we have our sums of squares, our mean squares, our degrees of freedom, our f-value, and our p-value associated with that. And we have our model, right? So that's our regression model there, and we have the error or residuals right here, and then here's the total. So sums of squares total is 30.5, sums of squares regression is 10.5, and sums of squares error is 20. Notice that 10.5 and 20 are going to add up to the 30.5. Additionally, we can take that sums of squares model and we can divide by sums of squares total to get our R-square. And so you can see we explain about a third of the variance, 34% of the variance in the road sobriety test scores is explained by the number of beers the individual had consumed immediately prior to the test. All right, so that's our R-square, and that's our descriptive measure of variance explained, so 34.5% of the variance explained. But we'd also like to get a test and see whether or not we're explaining significantly more than we might expect by simply capitalizing on chance. And so to do that, we've got to calculate our mean squares. So first we get our degrees of freedom. So 16 individuals, so n minus 1, 15 degrees of freedom for the total. We have, let's see, p minus 1 degrees of freedom for the model, and p is the number of parameters we're estimating. Here we have b0 and b1, so 2 parameters, and then we subtract 1 to get 1 degree of freedom. And then here's our degrees of freedom for the error, sums of squares error, and remember that's n minus p, so 16 minus 2 gives us 14 degrees of freedom. So we have our degrees of freedom for each piece. We then divide each sum of squares by its corresponding degrees of freedom, so 10.5 divided by 1 is 10.5, and 20 divided by 14 is 1.4. Those are our mean squares. Why do we care about those mean squares? Well, this mean squared error is going to be really important for all of our significance tests. It's also our sample estimate of the variance of the residuals around the regression line. But for right now, the inference test of primary interest is the overall model f-test. And so we take our mean square regression, divide by our mean squared error, so 10.5 divided by 1.4 gives us an f statistic, that's our f star, of 7.36. We look to see how extreme is a value of 7.36 if there was really no effect. And we see that the probability of observing an f star of 7.36 or greater if there were really no effect whatsoever of beers on psychomotor functioning on road sobriety test scores, the probability of this 7.36 or greater would be very low, so 0.002 roughly. So a very unusual f star were there really no effect, and so we conclude that in fact there must be some kind of effect. And we reject that null hypothesis and conclude that we have a significant effect of the consumption of alcohol on psychomotor functioning. Now we get a few other little bits of output down here. Here's our root mean squared error. That's just the square root of the mean squared error, and that's essentially the standard deviation of the residuals. We get the mean of the dependent variables, so that's the mean road sobriety test score is about 7.8. We get the coefficient of variation. That's not something I typically interpret much, but it's simple to interpret if you're interested in it. And then here's the adjusted R square, and that's sort of taking your overall model R square and adjusting for the possibility that you're capitalizing on chance to get a better estimate for how much variance might actually be explained in the population as a whole. So in our sample, we're explaining 34.5% of the variance. In the population, we might expect it to be closer to 30% of the variance explained. Then we turn to our parameter estimates, and here's our intercept. 9.6 is our B0, and there's our slope, negative 0.38. And notice that we're going to get t-tests associated with those, and we will talk more about those t-tests in the next episode. So I'm not going to go into those in detail right now. The only thing I'll note is that the t-test associated with the effect of beers has the same p-value, 0.0168, as the overall model f-test. And that's only true because we have just a single predictor in our model. If we had multiple predictors in our model f-test would test all of them simultaneously, and our t-test would be for each predictor singly. And so then the results would start to look different. But for this very simple model, in fact, they converge on the same p-value and represent a test of the same null hypothesis. Is there an effect, or is there truly no effect in the population? All right, so hopefully that little demonstration helps to make the ideas that we discussed earlier a little bit more concrete.
Alright, so I hope that was helpful for seeing what the analysis of variance table within the regression output is all about, what that overall model f-test is doing for you. Is again, we're just looking to see whether our model is explaining any variance at all in the outcome. And what we're going to talk about next time are the t-tests, right? So the t-tests associated with the sample estimates for the intercept and slope in the regression model. In the one predictor case, all right, our f-test is telling us whether or not our one predictor is explaining any variance, and so we saw that it's redundant with the test of that slope, of that v1. But when we move into having models with multiple predictors, that's where things get more interesting, is that's where that overall model f-test is going to diverge from those individual t-tests. The overall model f-test will be for the entire set of predictors, and the t-test will be for each individual predictor on its own. And so in the next episode, we'll look a little bit in more detail at the t-tests, and then we'll move on to the multiple predictor model. Thanks very much for your time.